All right, so the next set of questions we're going to go over, starting with 4, is let's say I had 2 groups, men and women, I have their gun ownership, and I want to build a 90% confidence interval for the true difference between gun ownership with men and women. Okay. So once again, I'll go to my formula sheet. I'm dealing with confidence intervals for the difference in proportions. So it's just going to be a matter of plugging in my values here, my sample proportions and sample size, and then looking up the z value that tells me the number of standard deviations where I need to go to get alpha over 2 in the tail. Okay. So if we had this equation, right, I'm going to start plugging my values. I got a sample proportion of what? 0.37 and 0.31. So let me make this bigger. So all I'm going to start writing this out is, actually, let's make sure group 1 was the 0.37. So 0.37 minus 0.31. That's what my confidence interval should be centered around. So when I'm looking at these potential answers, it should be centered around 0.06. Sure enough, 0.06 looks like it's right in the middle of all these. From there, add and subtract. We don't know that z value yet. It's the number of standard deviations where I need to go. So I'm looking at the standard deviation for the difference in my sample proportions, which is take each sample proportion times 1 minus that, divided by the sample size. Sample sizes are the same here, so that makes it a little bit easier. And now it's just a matter of looking up that z value that gives me alpha over 2 in the tail. I can't remember now what level of confidence we wanted, so let's go back and look at the problem. So we wanted a 90% confidence interval, so alpha is 0.1 divided by 2 is 0.05. I'm going to kind of use that shortcut, look at that student t-table and say, well, I know that if I want 0.05 in my tails, or on either side of my confidence interval, if I go to the very last row, that tells me the standard normal values. So I get 1.645, 1.645. Now it's just a matter of getting that entered into my calculator correctly. Okay, so if I open my Excel calculator here, 0.37 minus 0.31, right? Minus 1.645 times the square root of 0.37 times 1 minus 0.37 over 500 plus 0.31 times 1 minus 0.31 divided by 500, right? That should give me my, my lower bound, okay? So 0.0108, I can probably identify the correct answer just based off of that. 0.0108 rounded to the third decimal will be that 0.011. And then if I recreate this and just do where I add the margin of error, I should get that 0.109, okay? You then have the next question, which is what would the test statistic be if I'm got this two-tailed test and I had the same sort of problem? Well, first of all, I can rule one of these out right away. So if I'm looking at what I'm doing here, I've got the difference in my sample proportions, which should be centered around whatever that assumed true difference was, which we had, it was 0. So I found a sample difference, right? This kind of represents my sample difference here of 0.06. So that should translate to a test statistic. That's on the right-hand side. Remember, the student t-distribution centered at 0. So my test statistic here should be positive, and I wrote t here, that's wrong, because we're dealing with a proportion example. So if we're dealing with proportions, remember we had to use that standard normal distribution, so it's going to be a z value or a z statistic. Now what the actual value is, right? I'm going to go back to my formula sheet. And here's my test statistic equations. Oh yeah, here's that test statistic equation for my difference in sample proportions. Now, I know that it's going to be positive. Think about it this way. The difference I have in my numerator is a positive value, and the denominator represents a standard deviation. Standard deviations are always positive, so I can rule out this negative value right away. I probably can rule out B right away because this seems really small, right? When we're talking about proportions, finding a difference in a proportion of 0.06, I mean, the greatest difference I could ever find would be if one was 0 and the other is 1. So 0.06 isn't the smallest difference. 1.645 looks like a critical value. So my guess is if we enter this in our calculator, we'll get 2.002. Sure enough, if we do, I'm not going to kind of type that one out in Excel for you because I know that one is going to be that test statistic. Okay. So that's just a matter of plugging in our values to this equation here, right? Where we use P bar, find that, round to the second decimal, plug it in, plug in our sample size, the sample portion. Once again, these test statistic equations should be easy. I mean, I'm giving you the notation that we're looking for a difference in sample portion, so you should be able to identify that this is the test statistic formula of the three that you need to use. From there, problem 6, we have a similar as the last one. If you got the test statistic wrong, well, it's not going to go very well for you. But instead here, I ask you for the p-value. Okay. Well, we've got a two-tailed test, and I've got an assumed true test statistic of 1.45. So what I'm thinking about is I have this test statistic of 1.45. Usually, you would just look for the area more extreme than that and think that's my p-value. But for a two-tailed test, it would have been equally as likely for me to see something that went against the null on the other side, because now either side of this distribution, right, positive or negative sample differences, go against the assumed true difference, which was that true difference is just equal to 0. Okay, so I now have an alpha of 0.05 that I'm testing against, and I want to find the area that's in one of these tails and then multiply it by 2. So 1.45, we're dealing with proportions, so I know I can use the standard normal distribution. So I look up 1.45, 0.9265. Well, remember, the table always gives me the area to the left. I wanted the area to the right and then multiply it by 2. So this is what, 0.0365 times 2. So 0.0730, if I'm doing math in my head correctly here. All right. So 0.073 should be my p-value. Yeah, 0.0735. I might have made a mistake. What did I look at wrong there? Maybe I just made a rounding error. So 1.45, 0.9265. Oh, because I wrote down 625. I apologize there. 265, which makes this, wait a minute. Maybe I had it right the first time. 1.45, 0.9265. Oh, actually, I was wrong. So 0.9265 would mean that the area over here is 0.0735. Multiply that by 2. And we get 0.1470. This is why I shouldn't try to do math in my head, okay? So 0.1470, which would be answer C here. Now, if I had asked you for the rejection decision at an alpha of 0.05, if my p-value is less than alpha, we reject. Well, here my alpha is 0.05, my p-value is 0.147. That's not less than my alpha, so I would say I failed to reject there, okay? So that kind of goes through 6.